Hello, my name is Elanur Dursun, and I will be discussing Introduction to Prompt Engineering for high school students just like me. I'm an 11th grader and I go to American School of Dhahran. To begin with regard to my agenda, I'm going to discuss glossary like key terms and vocabulary. Then I'll continue on to large language models, prompt engineering, moving forward to prompting techniques, and I'll end it with example prompts for chemistry. I would like to begin with vocabulary and the glossary because I know that it will enforce a thought process getting going. Let's begin with artificial intelligence, which stands for AI. You've probably heard or seen it at some point in your life because it is really famous among us, especially right now. It's simply the science of teaching machines how to mimic human intelligence to perform tasks like learning, problem solving, and even decision making. A subset of artificial intelligence is machine learning, which stands for ML, and it's focused on algorithms that learn through experience or data. An example of this is teaching a computer to recognize handwritten digits through a data set. Then there's deep learning, standing for DL. It's a subset of machine learning, and it uses artificial neural networks to stimulate the way the brain processes information. For example, deep learning is used in facial recognition systems. A subset of that is neural networks, and you might have actually seen a neural network if you've done engineering research or artificial intelligence research online, and it actually looks really cool. It's inspired by the human brain, and it consists of layers of nodes, aka neurons, and it processes data to learn the patterns in it itself. Then there's the transformer, and it's a neural network architecture used in large language models for processing text data to understand as well as generate new text. Lastly, there's large language models, and large language models are powerful artificial intelligence systems on vast amounts of text data to generate human-like text responses. An example of this is OpenAI GPT-3 model. Large language model stands for LLM, and it's basically the probabilistic model that defines a probability distribution over the sequence of words to predict the next, if you guessed it, word in a sentence. Over here is the model itself. Now that we know about large language models, let's see how it processes text data. Okay, this comes into play through something called tokenization, and it's very simple. It's simply the breaking down of text into smaller units, which is known as tokens, like words or subwords for processing by large language models. So, if we look at this picture below, this is a text, right? But the reason why there's colored portions is because each of those colored portions are tokens. For example, if we read, we can see open is a token, AI is a token, apostrophe S is a token, large is a token. Helps us break down the words. Embedding is a process that represents words or tokens and converts it into numerical vectors in machine learning models. Embedding makes it easier for computers to understand relationships between concepts. Similar we can see relationships of words that are similar or close to each other, and that's what is being embedded in the first place. For example, here if you read canine companion say is being embedded into wolf, or feline friend say is being embedded into meow. So far we know that the input value became tokenized, then we embedded each part to convert it into vectors. Now these vectors are going to be applied to inputs of transformers. Okay, what I want to begin with here is positional encoder, and as you can see through the blue arrow, this is where it occurs, and it's simply it provides information about the position of the word or token or subword in a sequence. For example, adding positional encoding to word embeddings. If I say the sky is blue today, the position of the word sky would be second. That's what we know. Moving forward, there's also multi-head attention, and that can be seen here through the green arrow. It allows a model to focus on different parts of the input sequence simultaneously and analyze different aspects of a sentence in parallel. Moving forward, there's also the encoder, which can be seen here through the orange arrow, and its primary function is to transform the input tokens into contextualized representations. This can be seen here through, if I tell you bank, when I tell you bank, what do you think? You think of money. But if I tell you riverbank, you think of water. This is why encoders are important because you need to make sure that the context you give is understandable. Moving forward, there's also the decoder, and it's a component of a transformer that generates output sequences based off of the encoded information. That can be seen here through the top arrow. Well, what can large language models do? They actually have a lot of capabilities, and here are four. First of all, language understanding. They can understand the meaning of the words in the text data. There's also language generation, which is creating or generating contextually relevant and high quality text data. Okay, the third thing that I want to discuss is the knowledge intensivity, which is extra knowledge from large amounts of documents faster. Fourthly, there's reasoning, which is solving problems that require mathematical, logical, common sense reasoning. These are powerful capabilities of large language models. However, when it comes down to harnessing these capabilities, we need a way of interacting with the models efficiently, which is where prompt engineering comes into play. Prompt engineering is about developing and optimizing interactions prompts to efficiently use language models for different applications. Prompt engineering skills help to better understand the capabilities and limitations of large language models. Simply speaking, prompt engineering is the art of asking questions to maximize the utilization of large language models. Well, what should the prompt contain? Here are some elements. Firstly, we already know this in the real world instruction, a specific task or instruction you want the model to perform. Simple. Then there's context, which is just external or additional context that can steer the model to a better response. Moving forward, there's input data, which is the input or question that we're interested in finding a response for. Lastly, there's the output indicator, which is the type or format of the expected output we want in the end. One of the things that I personally find amusing are prompting techniques. For example, there's zero-shot prompting, which is where a language model generates responses to prompts that it hasn't really seen during its training. Then there's few-shot prompting, and in few-shot prompting you provide a small number of examples to fine-tune a language model for a specific task. Then there's chain of thought prompting, which is a little more complex, and it involves constructing a sequence of prompts in a chain to guide a language model to a series of logical steps. This prompt specifically is kind of complex because it requires some capabilities like logical and common and mathematical thinking, since you have to provide it steps. Lastly, there's meta prompting, which involves the designing prompts that help language models adapt to new or even unseen tasks more efficiently. To go into further detail, here's a zero-shot prompt example. Zero-shot prompting, as I discussed before, allows large language models to generate responses without explicit training on that prompt. For example, the prompt describe the properties and applications of carbon nanotubes. We would expect the output to be an informative description of carbon nanotubes, unique properties, and their diverse applications in fields such as electronics and material science. Moving along, I would like to talk about few-shot prompt examples, which involves providing a limited number of examples to fine-tune the large language models for a specific task. For example, given the prompt The following chemical reaction examples predict the products of the reaction H2 plus O2? Question mark. We would expect the output to be like the large language model predicting the products of the reaction based off of the provided examples, which is what we gave H2 plus O2, showcasing the ability to generalize patterns in chemistry. I personally like the chain of thought prompt example like the most out of the four because it's not too hard, but it's also not too basic, and it involves a little bit of everything. The chain of thought prompting strings a series of prompts together to guide the large language model's thought process. For example, you give a prompt chain, define exothermic reaction, provide an example, explain its significance in material science. We're giving it step-by-step prompts. So we would expect the output to say, oh, a coherent sequence of responses detailing the definition, and then an example, the importance of the exothermic reactions in material science. And this is why I find it pretty cool because it's kind of a little bit of everything. Coming close to the end, now we have meta prompting, and it involves designing prompts to help large language models adapt to new tasks efficiently. For example, we give the meta prompt, given a list of elemental properties, predict the chemical reactivity trends across a periodic table. We would expect the output to be like, oh, the large language model analyzing the elemental properties and inferring the trends in the chemical reactivity, showcasing its adaptability as well as its interference capabilities. To access a language model, we can use the OpenAI Playground, in which you can try different prompts. For example, here I have different models and response formats, functions. Right now I'm on GPT-40 and etc. I did the best I could as a high schooler to explain prompt engineering, and I hoped you learned something. I tried to make it fun and also easy at the same time. I'm really honored to have been invited to this ChemIndex 2024 conference program committee to present this transformative potential of prompt engineering in chemistry and material science. Thank you for providing this platform and believing in the power of young minds, and for inspiring a passion for chemistry and unwavering support. Thank you so much for your time. Have a good day.